In this video, I'm going to walk through the process of figuring out whether there's a more effective way to heat my house than with its boring and inefficient electric resistance boiler. My house is in coastal BC and has a lot of unique features, so some of my analysis won't apply to you, but I'll try and explain the general background as I go along. The video has three major parts. First, we can't analyze a conservation measure without knowing how much it's going to be used, so before we can even start, we need a basic model of the house's heating load. Secondly, I'll talk about how I chose to model the house and the various energy flows that make up the heating model. This will give us a reasonable picture of what each measure will do. And finally, we'll use some basic microeconomics to show how we use the change in consumption to evaluate net savings over the long term. Every conservation measure I could think of is time dependent on a scale of hours, so we need an hourly model for heating load. Unfortunately, if you look at my hourly demand profile with and without heating, it's pretty clear that the heating demand is all mixed up with the load for, well, everything else. The top histogram here shows how often my house is at any given level of demand. Having seen winter and summer load profiles, we can be confident that the left peak at about 1 kilowatt is base load, and the right peak at about 2.5 is heating. The lower histogram is summer demand, which ought to be an excellent reflection of base load. And if you disregard my vacation on the left, we have a very normal-looking distribution, just the thing to gladden the heart of any data cruncher. The simple path is to just subtract mean base load and believe that what's left is heating. Unfortunately, that leaves behind the upper tail of base load. This is ugly, but after trying everything else in my bag of statistical tricks, this is the one that actually modeled the real-world house reasonably well. So, quickly confirming that outside temperature is the only thing that matters, we compare our numerical heating load to heating degrees and decide that we're on the right track. Once we've convinced ourselves that heat loss ought to be fairly linear with delta T across the wall, we go looking for a linear relationship, and without too much trouble, we find one that actually matches the house demand reasonably well. My basic question is whether to get a heat pump, a solar collector, or both. To do that, we need to know how they work together in context. So I hunched over my desk and created a model that allows conservation devices to operate sequentially on an hour-by-hour basis. The core of my model is the hourly state of the house. It boils down to this data set. In theory, any measure can modify any parameter. In practice, they most just modify the residual load. I don't have time to go through all of my models, but vacuum solar tubes are particularly interesting. Basically, they're greenhouses, but for water. They let visible and UV light in, and don't transmit very much infrared back out. I found a Canadian price and went to work. $1,600 is expensive, but vacuum tubes work well even when there's a big delta T from the water to the outside air. By definition, that's important if you want to use them for heating. The papers and websites I reviewed suggested that at my latitude I should be using an angle of about 40 to 50 degrees from horizontal. That didn't feel right. I don't know about you, but I mostly heat in the winter when the sun is low. Optimizing to maximize the amount of heat saved rather than collected, I found the best angle was 70 degrees. That seems high, but I believe it. The sun never goes above 25 degrees for the 3 coldest months of the year. With 3 square meters of collector area at this angle, I would save about 16% of my heating load, assuming minimal pipe losses. It's better to reduce demand than to optimize consumption, and night setback is the only measure I have that changes heating load. I didn't think it would work because my house has a lot of thermal mass. In the upper plot here, you can see the setback temperature is never reached. But it turns out that an 18-degree setback for 8 hours has almost 7% savings. That seems unreasonably high, but remember, if it's 12 degrees outside, reducing from 22 to 18 is fully 40% of the delta T. In this chart, heating is proportional to the area between the orange squiggle and the top of the pink square wave, so the savings are the area above the blue triangles. Check it out! The colder it is, the more likely you'll save enough money to go buy a sweater. None of this is rocket surgery, but if it costs money now to save money later, should I do it? We can figure it out with discounted cash flow analysis. That boils down to the idea that interest, inflation, and risk make future money worth less than present money by a real concrete amount. We call it the discount rate, and it compounds just like interest. I like to use 7%, a rate of return that I'd be happy to invest at. Let's apply it to the value of saving 1 kilowatt hour of electricity per year forever. Hydro is likely to escalate at 3.5%, so our net discount rate is the remaining 3.5%. Clickety-click, and the growing perpetuity starting at 13 cents is worth about $4. We can do the same thing with the cost for my solar project. The discount rate over a 20-year period is 287%, so $700 today is worth the same as $2,000 in 20 years. Similarly with maintenance. Adding up all the costs, $4,600 is the total present value of the costs of installing and maintaining the collector forever. We've established that it would save around 900 kilowatt hours at $4, so our net project value is about $1,000 in the hole. If you don't believe in forever, here's how the spreadsheet would look over 60 years. Well, that was depressing, but not surprising. My heating budget just isn't big enough to pay for anything fancy. To wrap things up, I ran all possible combinations of the 3 interesting models: solar collector, a storage tank to receive excess heat, and a heat pump. Each combo has to be run as a group because energy saved by one isn't available to be saved by the next. Then I applied 10 years of field experience to estimate present life cyclical project costs for each measure and translated them into present value costs. Then I netted them all out. I was frankly a bit surprised to find that I can actually save money by installing a heat pump. Wrapping up, the main things to learn here are 1. A simple heat load model will work well enough. 2. Pick the low-hanging fruit and ignore the rest. 3. If you're not spending much money, it's hard to save money. And 4. I should get a quote on a heat pump. Thanks for watching.